Welcome to Homework Lib.
We have some data here. We have retail prices of electricity in 2018 and 2019 for the same counties. So we are going to be performing a paired t-test. Because these are not independent samples, a piece of data from 2018 matches up directly with a piece from 2019. The same county, different year. So it's a paired t-test. And we're interested in looking at the mean difference. Now, let's start with stating our hypotheses. The null hypothesis represents no change, no difference. It always gets some kind of equal sign. Here, it represents that the average the average is 0, the average difference. So mean difference is 0. For the alternative, we want to know if the price has changed. So not saying it's higher or lower, we're just saying it's different. So the mean is not 0. Could be positive, could be negative, either would work here. So this is going to be a two-tailed test. Now for our sample data. We need number of pairs, mean difference, and standard deviation of the differences. So we need to get the differences. So for example, 2018 we have 12.64 minus 13.86, we get minus 1.22. And I will just state the data here. So we've got minus 1.22, that is 1.77. Of course, it's a lot faster if you just put this into software like Excel, make that do it for you. Same for actually getting the descriptive statistics. So 1.78, 0.35, 0.59, 0.69, 1.45. So there's our data set. Those are the differences. Now for the mean and standard deviation, I'm going to keep using Excel. I need average and standard deviation dot sample, because it is a sample. Now the number of pieces of data is 9. We have 9 pairs here. The mean is 0.98, where the 8 is recurring. The standard deviation is 1.0105, and so on. I've got the exact value. Finding the descriptive statistics, like mean and standard deviation, are very much busy work at this point. You should know how to do that, but it's fine to get a calculator to do it for you. Now, for the hypothesis test. To test our claim, we start by assuming the null hypothesis is true. Then we look at our sample data. If I were to take every sample of size 9, take the means and plot them out, I would see something approximately normal, since we know that the paired differences follow an approximately normal distribution, and under the central limit theorem, as sample size increases, the sample means become more and more normally distributed. So the average difference for a sample of size 9 belongs to this approximately normal distribution. Its mean is the same as the population mean. Its standard deviation is sigma over root n. We don't know sigma, the population standard deviation, which is why we have to use our sample standard deviation and therefore a t-test instead of a z-test. Now I'm interested in where my sample mean would fall on this curve. The mean here is 0, since we think the mean difference is 0. Would my value be, say, here? It's not 0, but it's pretty close. The chance of this happening is pretty high. I could believe that our sample belongs to a distribution with a mean of 0, and that the null hypothesis is true, so we don't reject it. But if my sample mean is way out here, I would say, if the null hypothesis is true, this is really unlikely. Therefore, I don't think it's true. So where are ours? Well, we're going to find the test statistic, which is basically the z-score of our sample mean. So it will tell me where on this curve it falls. Calling it t because we're going to be using s instead of sigma. But the same kind of idea applies. You take the raw value, you subtract the mean, what we think the mean is, and divide by the standard deviation, which should be sigma over root n, but we have to use s over root n. Okay, so let me just get this. So we've got s over 3 and 0.98 recurring on the numerator is 2.936 to 3 decimal places. Okay, so there's our test statistic. Now I'm going to get the critical values. So the level of significance here is 5%. That means if we see something 5% or less likely, that's significant enough for me to say, okay, that was really likely. I don't think the null hypothesis is true. The critical values are the cutoff points on the relevant t-distribution where you go into that unlikely territory. You go into the rejection rates. Now I mentioned this is a two-tailed test. Our sample mean could be much higher than 0 or much lower. Either would be interesting here because we're just looking for a difference. And we split alpha equally between the tails. So I'm looking for a t-value with tails of 2.5%. We also need degrees of freedom, which for a paired t-test is number of pairs minus 1. So 8 degrees of freedom. And that is 2.306. You can use Excel for this as well. There's a function. Let's put it up here. Equal t.inv, inv dot 2t. You just put in alpha and the degrees of freedom. The 2t for two tails, make sure that you get the tails of half of that. So our test statistic is more extreme than the critical values. This is plus minus, there's two of them. So our value is in the rejection region. It is significant. So we can say that we reject the null hypothesis. Let me make some space to do that. Reject null hypothesis. And we can support the economist's claim. They think that there's been a change. We agree. Because we don't think the mean difference is 0. We think it's something else.